Okay. So page 24, we're going to start with geometric sequence. So geometric sequence. Well, in unit 4, it says we first encountered a special list of numbers, which we ended up calling an arithmetic sequence. We know that if a sequence is arithmetic, what are we doing? If it's arithmetic, we're doing what? Adding or subtracting the same amount each time. Okay, we're adding or subtracting. So tell me what this recursive definition means right there. We've done a ton of arithmetic sequence. Tell me what that recursive definition means right there. A of 1 equals 5, A of n equals A of n minus 1 plus 3. Perfect. Plus 3 for you. The initial value is 5 and we add 3. So Noah, can you tell me what the first, I'm writing down your plus 3. Can you tell me what the first 4 terms are? Start with A of 1 is 5. Yep. Yep. 8 plus 3 is 11. Keep going. That's right. Perfect. 5, 8, 11, and 14. 5, 8, 11, and 14. Okay. Find the value of A of 20 without listing all 20 terms. Well, that means I need to know the explicit formula. So remember the rule for the explicit formula. It's right on the board. It says A of n equals your A of 1, which is your first term. What's our first term in our sequence? 5 plus the common difference. What's my common difference? 3 times n minus 1. So if I want to figure out what the 20th term is, I have to say, well, A of 20 equals 5 plus 3 times 20 minus 1 is 19. So let's see, 57 plus 5 is, what do we get? 62. Okay, 62. So clearly arithmetic sequences share many characteristics as a linear function. We talked about that. In fact, an arithmetic sequence is a linear function. We just call it what type of linear function? Begins with a D. You wish, bud. What do you think? What's that word? Discrete. Very good. What does it mean to be discrete? Discrete is what? Say again. Not hidden. Yeah, but what does it mean in terms of this? Do we connect the points or not? When we have a function that's a discrete, is it gonna, because it's a discrete linear function, do we connect the points to make a line, or is it just a bunch of points or dots? Yeah, we just leave it as points. We do not connect them. No line. No line, okay? That's what discrete means, okay? Well, exponential functions have their own discrete version, and they are called geometric sequences, which is what we're working on today. They have a very simple recursive definition. Notice that you have to start with the first term. You have to start with A of 1 equals some number. Whenever we write that, we just let a lowercase letter in the alphabet equal some number. So I just use K. And then to find the recursive formula, we say A of n equals A of n minus 1 times R. A of n minus 1 times R. And I actually, when I do this, I actually write it like this. I honestly actually write it as A of n equals R times, I put the R first, just because it makes more sense in my brain. But anyway, so for each of the following geometric sequences, we have to find what R is. And R is called the common ratio. So in a linear function or a arithmetic sequence, we have a common difference. In an exponential function or geometric sequence, we have a common ratio. And remember that when we think about exponentials, we have a multiplier, right? So this means that we're multiplying by the same term. This common ratio is a multiplier. So tell me, what did I multiply 2 by to get 6? What did I multiply the 2 by? 3. So that means that R, my common ratio, is 3. So if I keep that pattern, what is 18 times 3? And 54 times 3? Good job. Okay, let's look at our next example. So what am I multiplying? What did I multiply 4 by to make it equal negative 20? Good job. So R is negative 5. Negative 20 times negative 5 is positive 100. 100 times negative 5, Jaden, is? Times negative 5. And negative 500 times 5 is? Perfect. Okay, let's look at the next one. Remember, we're looking for a common ratio or a multiplier. That doesn't mean that it can't be a fraction, okay? So what are we doing here? Yeah, my common ratio is 1/2 or 0.5. So what's my next term going to be, Aiden? And the one after that? Perfect. God bless you. How do we feel about that? Good? Yeah? Okay. So now we're going to look at a recursive formula and we're going to make some predictions about the next numbers in our list. So it says, as with an arithmetic sequence, we should be able to predict any particular term in the geometric sequence by thinking about how many times we have to multiply by the common ratio. So it's starting us off with this recursive rule. So remember that the recursive rule always tells us the first term, and then it always is going to give us our common ratio or common difference. So it says, use your recursive rule to find the second term, the third term, and the fourth term. And we're going to write it out as a product. Well, if the first term is 3, and my common ratio, it says, is 2. If I want to find the second term, I'm just taking 3 times 2, and that's going to give me what? 3 times 2 is 6. If I want to find the next term, the third term, I'm going to take 3 times 2 times 2, which is 12. And if I want to find the term after that, because it's asking us to like show it using products, right? I'm going to take 3 times 2 times 2 times 2, which equals 24. Okay. So this tells us how to set up. Remember, we did this with an arithmetic sequence. This tells us how to set up our explicit formula. This tells us how we're going to set up our explicit formula. So this is what this says. If I want to find the explicit formula, so that's what we're going to write out first. This is going to be our explicit formula for our geometric sequence. If I want the explicit formula, it looks like I have to start with my first term, right? And then it looks like I multiply it by my common ratio. But if I'm looking for the fourth term, how many times do I multiply by the common ratio? Listen to what I said. When I wanted the fourth term, how many times did I multiply by the common ratio? How many circles are up there? 3. If I want the third term, how many times do I multiply by the common ratio? So how do we show 1 less? N minus 1. And it's a power, right? This is 2 times 2 times 2, or 2 to the third power. So the n minus 1 is actually an exponent. the n minus 1 is actually an exponent. So now it's asking us to find the 20th term. So that's b of 20 equals, well, what was the first term in this sequence? What was b of 1? 3 times, what is my common ratio in this sequence? 2. And if I'm looking for the 20th term, n minus 1 is what? 19. So I have to take 3 times 2 to the power of 19 to find the 20th term. 3 times 2 to the power of 19. Starts off with 1 million. Who's got it for me? 572,000. Keep going. Good job. Good job. Jaden, I want you to know that I threw some points your way too because you volunteered a ton. So 1,572,864. 864. Okay. Why does that seem to grow so much faster than like an arithmetic sequence? Because it has an exponent. Exponents grow faster than linear functions. Exponents grow so much faster than linear functions. Okay, let's go over to the next page. We've got like 2 examples and then we're done. 2 examples and then we're done. Okay. So one thing you might have noticed in the last exercise is how quickly a geometric sequence grows. Let's take a look at a classic problem. You've just won a very strange lottery. The lottery promises to give you money each day for 30 days a month based on one of 2 options. Option 1 says you can receive $1,000 on the first day, $2,000 on the second day, $3,000 on the third, and so on. So if I think about option 1, let's just talk about it. My initial value is 1,000. And I'm adding, my common difference is 1,000. Every day they're adding 1,000 more, right? Does that make sense? Okay. Let's look at option 2. Option 2 says you can receive 1 penny on the first day, 2 cents on the second day, 4 cents on the third day, etc. This is a geometric sequence. So I'm going to call it B. B of 1, my initial value is 0.01. You start off with a penny, and your common ratio, it looks like each time I'm multiplying by what? How many times is it getting bigger? 2 times. Okay. So it says, of the 2 options, which would result in the larger payout on the 30th day only. So we just have to figure out the 30th term. That's what it's asking us to do. It's asking us to figure out the 30th term from both. So we have to write the explicit formula. So option 1, explicit formula. Let's start with that. Okay. So option 1 is linear. We need to know our first term. So I know A of n, explicit formula equals my first term. I'm going to write it out first of all, plus my common difference times n minus 1. So what am I plugging into this equation? We're writing it for the first example, option 1. What is my first term for option 1? We wrote it. A of 1 is what? 1,000. Plus my common difference, which was, what am I adding each time in option 1? 1,000 times n minus 1. Okay. I'm not going to find the 30th term yet. Let's write the explicit formula for option 2. So for option 2, the explicit formula, well, it's a geometric sequence, right? So if I want the explicit formula for a geometric sequence, A of n equals A of 1 times r to the power of n minus 1. So let's plug in those values. So what is my first term? Geometric sequence, option 2, what's the first term? 0.01 times what is my common ratio? To the power of n minus 1. So now I'm going to slide up and we're going to calculate. We need to find the 30th term for both. We just want to know what the payout is going to be on the 30th day. Hang on a second. So on the 30th day, this would be 1,000 plus 1,000 times 29. So what's my payout going to be on the 30th day for this one? Someone do the math. What's 1,000 plus 29,000? Yes. On the 30th day, my payout would be $30,000. That's a good payout for one day of work, right? Okay, let's look at the second option. Let's see, A of 30 equals 0.01 times 2 to the, what power am I taking that to? 2. The 29th. Oh my gosh. So someone put that into your calculator and tell me how much money would my payout be on the 30th day if I chose the geometric sequence? I think that you forgot your decimal. So I think it's 5 million, right? Doesn't it start off with 5 million? Keep going. Did you put a decimal in when you calculated that? Point. Okay. But when you calculated, did you put 0.01? When you multiplied, I'm asking, did you put 0.01? Okay. So it should be 5,368,709.12. Doesn't sound like very much getting 1 penny a day and having it double, but which one would give you the better payout? Yeah. Option 2 is the one that you're choosing, right? Yeah, you would absolutely choose option 2. It's the better payout. Okay. Graphs of geometric sequences look just like graphs of exponential functions. So it says here, our first term in this geometric sequence, our first term is 16. My common ratio, R, is 1/2. So that means that the second term is, what's half of 16? 16 times 1/2 is 8. 8 times 1/2 is 4. 4 times 1/2 is 2. 2 times 1/2 is, and 1 times 1/2 is, or 1/2. Yes. So we need to graph those. We need to graph those ordered pairs. So when A is, like when my sequence term is 1, my output is 16. And I had to count all the way up to here. I'm just counting by ones. This is 16. When I had an output of 2, what was that? 2, 4, 6, 8. Okay, 3, my output was 4. 4, my output was 2. 5, my output was 1. And when n was 6, my output was 1/2. And that's going to just keep getting much smaller, much closer to the x-axis, but never going over. Okay, much closer to the x-axis, but never going over. This is 8. This is 4. This is 2, 6. I don't know if you guys need to number it, if that'll help you. Okay. So your homework is the last 2 pages, page